Hello guys, so welcome to my session. Today I will be talking about the quantum switching and the quantum merge sorting from the applied physics. So myself is Gautam from Institute of Aeronautical Engineering of roll number 219518055 of CSE A section. So now let's jump on to the topic. So coming to the contents of this topic. Today we will be talking about the various contents from the introduction of quantum merge sorting and quantum botonic merge, next quantum merge sorting and the performance evaluation of quantum merge sorting, and then we will be talking about introduction to quantum switching, and the next is quantum switching currents, the garbage be cleaner, and the performance evaluation of quantum switching, and lastly the conclusion of this topic. So now let's get into the first topic of this session. So now let's talk about the introduction of the quantum merge sorting. So the quantum computation and the quantum information science QIS that study the exploration of quantum mechanics, which provides us the advanced tools to solve hard problems in traditional Turing machines. So the fundamental element in the quantum field can be any particle with two states that coexist together, such as photon, atom, electron, or subatomic particle. So all of them are under the nanoscale. Thus, QoS is often considered to be a basis for further research and innovations in the further development of nanotechnology. So, in literature, many outstanding algorithms have been developed to illustrate the quantum-based computers are more powerful than the traditional computers. So, for example, S.H. Shor presents a quantum algorithm that factors a composite integer for exponentially faster than the classical algorithms do. And the Grover presents a quantum algorithm that searches an element for an unstructured list polynomial speedup over classical algorithms. Due to its potential impact and significance, QoS has drawn more and more attentions in the recent decade. One of the most important applications in QoS is the quantum communication, that is a mechanism for transferring quantum data from one location to another. Among them, quantum wire is one of such mediums for transporting quantum information. At present, many remarkable research issues based on the quantum wire configuration, such as quantum teleportation, quantum cryptography, quantum repeater, and quantum networks have been raised. These results have driven the QoS field further into the real world applications. Many views of the future of QoS indicate that the need for basic quantum wire components would have become more essential due to the explosive growth of quantum devices. So, as shown, in order to ensure any two quantum devices can communicate quantum data with another, it is necessary to employ a quantum wire between them. So, however, this results in a fully connected quantum network that would require O and O into wires to construct. where n is the total number of quantum nodes. So now let's get into the next topic. So now let's talk about the quantum Betonic merge. In this subsection, we start out to present the quantum Betonic merge to combine two sorted quantum lists into an ordered sequence. The skeleton for quantum Betonic merge is depicted in figure 8 as shown. The quantum Betonic merge can be further split into two components, the reverse operation and the Betonic sorter. In this subsection, we start out to present the quantum Betonic merge to combine two sorted quantum lists into an ordered sequence. The skeleton for quantum Betonic merge is depicted in figure 8 as shown. The quantum Betonic merge can be further split into two components, the reverse operation and Betonic sorter. Quantum Betonic sequence is defined as a quantum sequence that is either monotonically increasing and then monotonically decreasing, or monotonically increasing and then monotonically increasing. Besides, a monotonically increasing or decreasing sequence is also a Betonic sequence. The quantum circuit of the quantum Betonic sorter is designed for sorting any quantum Betonic sequence. The basic idea of quantum Betonic sorter for sorting any Betonic sequence is to separate input Betonic sequence into two Betonic sequences. And by recursively performing the quantum Betonic sorter in parallel, we can sort the quantum Betonic sequence ultimately. More precisely, as drawn in figure 9, the former part of quantum Betonic sorter N is made up of n by 2 comparator gates. It is clear that these two output sequences are both 68 Betonic and each number in the first half is smaller than that in the second half. So thus by following the same procedure continuously, we can get a sorted sequence. Ultimately, as a result, we can sort any Betonic sequence by performing the quantum circuits in figure 9. The quantum Betonic sorter only accepts Betonic sequences. However, it can be seen from figure 9 that the output sequences from the division phase are not Betonic but two sorted sequences. Therefore, it is necessary to employ the reverse operation to convert the ordering of one sorted sequence. Consequently, the output turns out to be a Betonic sequence. So this is the architecture for the Betonic sorter and the merge. So you can hope you can understand this picture as it's very complicated. So now let's talk about the quantum merge sorting. In this subsection, we illustrate the QMS algorithm for sorting 8 quantum elements. As mentioned above, the QMS algorithm is a recurrence in structure. Thus, after recursively expanding the QMS algorithm, we can get the infrastructure constructed by the quantum Betonic merge as shown. In addition, as depicted in figure 14 in the previous slide, for each quantum Betonic merge, it can be implemented by executing n by 2 comparator gates and two quantum Betonic sorter n by 2 in parallel. Thus, after replacing the quantum Betonic merge by the circuits in figure 14 in previous slide, we can obtain the construction as depicted in figure 16. Finally, as drawn in figure 9, quantum Bitcoin sorter is also a recursive construction and can be performed by applying n by 2 comparator gates and two Bitcoin sorter n by 2 operations in parallel. Thus, we can substitute figure 9 into figure 16 and then entire QMS circuits can be carried out as shown in figure 17. So now let's jump on to the next topic. So now let's talk about the performance evaluation of quantum merge sorting. In this subsection, the performance of QMS algorithm is studied. Let NQ of n, Nm of n, and Ns of n denote the number of comparator gates that are needed to implement the QMS merge of n and sorter of n circuits respectively. So for n greater than 1 and nq of 1 equal to nm of 1 equal to ns of 1 equals 0 as n is greater than 1. So by applying the Master theorem to the above equations, we know that nq of n equal to n log n. From 9, it can be seen that the QMS algorithm still requires n log n queries to comparison gates that matches the lower bound by Hoyer. However, the purpose of QMS algorithm is not to outperform other quantum sorting algorithms, but to provide an efficient parallel quantum computation to decrease the whole running time of quantum sorting algorithms. So let TQ of n, Tm of n, and Ts of n denote the time complexity of the QMS of n, the merge of n, and sorter of n circuits respectively. So similarly, based on the equations 3, 4 and 5, it can be for n greater than 1, where Tc of k is the time complexity of the comparator gate with two k bit input numbers, and Tq of 1 equal to Tm of 1 equal to Ts of 1 equal to 0. In other words, the QMS algorithm achieves the polyalgorithmic time complexity, so it can be employed in constructing some quantum instruments with critical time delayed delays such as the quantum switching. The details of the quantum operations required to implement the quantum switching are described in section 4. So now let's talk about the introduction of quantum switching. In this section, the proposed quantum switching to avoid the fully connected networks is presented. The quantum switching is designed to permute each input data to its corresponding destination port dynamically. In addition, since quantum qubits cannot be replicated, the multicast service is not supported by proposed quantum switching. In other words, each input data is allowed to have exactly one destination port. On the other hand, if there exist two or more input qubits with same destination port, it would result in the so-called output collision. Therefore, to prevent the quantum switching from the output collision, we only consider the case that each input data and output have one-to-one mapping. So in figure 19 shows the sketch of the proposed quantum switching architecture. As shown, the quantum switching consists of two sectors, switching sector and control center. The switching sector is the only responsible for permuting all the input qubits into their corresponding output ports, and the control sector is responsible for controlling the switching sector so that the switching sector can accomplish its task correctly. So actually, the data permutation in switching sector is dominated by the control registers. More precisely, we consider the case that there is a qubit QI input to the IO port PI with the destination port PJ. To fulfill the switching task, we set the corresponding control registers. Set of BJ. After we set all the control registers by performing the quantum switching, all the input data would be switched to the corresponding destination port correctly. In essence, the quantum switching can be viewed as a quantum mass sorting algorithm that sorts all the input qubits QI into an increasing order by their corresponding destination port numbers here. So as a result, the quantum switching architecture can be constructed easily by using the QMS algorithm presented in this section 3. The details are described as the follows. So now let's talk about the quantum switching circuits. Before we present how quantum switching can be constructed by using the QMS algorithm, we define a particular partial comparator gate for the quantum switching first. As shown in figure 20a, the partial comparator gate only compares the register C1 with the register C2. So otherwise the partial comparator gate flips the workspace qubit state, that is changes the state from 0 to 1 and swaps the registers C1 and C2 and the qubits Q1 and Q2. Actually, the partial comparator gate can be seen as a comparator gate appended with a controlled swap gate. Quantum switching can be seen as a kind of quantum sorting algorithm that sorts each input qubit by its destination port number. The first step of constructing the quantum switching is to establish the QMS and circuits in the control sector. And by then, for each comparator gate in the control sector, we append a controlled swap gate on the corresponding input qubits. A example for implementing the quantum switching with 4 IO ports is illustrated in figure 21. As mentioned above, the quantum switching can be done by first constructing the QMS 4 circuits in the control sector as in figure 21. The afterwards a control swap gate is appended to each comparator gate on the corresponding input qubits as drawn in 21b. For the comparator gate applying on the registers C1, Ci and the Cj. A control swap gate is performing on the input qubits Qi and Qj. After that, the quantum circuit is obtained as shown in figure 21b. So furthermore, it can be seen that after performing the quantum circuits in figure 21, each input qubit is permitted to its corresponding destination port. So you can see in this figure it's about the quantum switching which I have talked in the previous slides. Hope you understand this figure and get it. So now let's talk about the garbage bit cleaner. In addition to switching sector and control sector, It is necessary for the quantum switching to implement a garbage bit cleaner. As depicted in the figure 20, whenever we employ the partial comparator gate, we require an ancillary workspace to make the partial comparator gate revertible. However, those qubits would become garbage bits after the quantum switching. Therefore, to utilize those workspace qubits more efficiently, we implement a garbage bit cleaner to clean those garbage bits so they can be reused in the next round. So, the garbage bit cleaner can be roughly seen as the inverse of the control sector. Since the control sector is primarily constructed by the QMS algorithm, the garbage bit cleaner can be done by implementing the reverse of the QMS algorithm. So we employ the following methodology to build the inverse of the QMS operation. The first step is to implement the QMS circuit in the reverse order. And the second step is to replace each comparator gate by the inverse of the comparator gate. An example for implementing the inverse of QMS is illustrated here. We define the quantum logical gate drawn in figure 23a to be inverse of the comparator gate. It is clear that, as shown in figure 23b, the inverse of the comparator gate can be constructed by applying the comparator curve circuits in figure 5 in reverse order. Now we can start out to build the garbage bit cleaner. Figure 24a shows the QMS quantum circuits to construct the inverse of the QMS operation. So we first implement the QMS circuits in reverse order as depicted in figure 24b. So after we replace each comparator gate in figure 24b by the inverse of the operator comparator gate, we get inverse of the QMS for CAM as shown in figure 24c. By substituting the quantum circuits in figure 21b and figure 24c into the quantum switching architecture in figure 22, we can get the quantum switching circuits as depicted in figure 25. So now let's talk about the performance evaluation for quantum switching. In this subsection, the performance of the quantum switching is studied. So we define three factors to evaluate the effectiveness of the quantum switching: space complexity, implementation complexity, and delay time complexity. Each of these plays an important role in evaluating the practicability of a quantum instrument. Space complexity and implementation complexity refer to the complexity in accomplishing the quantum instrument. Delay time complexity represent, represents the running time in execution. In practice, the delay time complexity is more critical than the space complexity and the implementation complexity, since the proposed quantum switching is designed to be reused. The space complexity C of n for the quantum switching contains n input qubits and n control registers and extra workspace qubits. Since each control register is responsible for storing the destination port number of the corresponding input qubit, it requires at least log 2n qubits. As for the number of workspace qubits, because we have to employ an additional workspace qubit for each partial comparator gate, and it can be seen from 9 that the quantum switching requires performing n-log-n comparator gates. We need n-log-n workspace qubits in total consequently. C of n n log 2 of n into n log n into n log n. On the other hand, it is clear that quantum switching with n I by O ports has to be able to handle impossible cases due to n equal to 2n log n 22. It is unavoidable for the quantum switching to apply n log n control bits to specify each possible switching case. This matches the space complexity of proposed quantum switching. So the proposed quantum switching is verified to be efficient in space consumption. It can be seen as that the quantum switching with an I dot O ports is composed of n log n partial comparator gates and n log n inverses of comparator gates. In addition, as shown in figure 20a, each partial comparator gate contains a comparison gate and log 2 and 1 control swap gates. The quantum for this is the figure for the process to implement the garbage bit linear, and the figure 25 depicts the entire quantum switching currents. So now in conclusion, because many breakthroughs in quantum communication have been discovered, this results in the fact that the demand for establishing the communication networks becomes more and more urgent. To save the cost in building the quantum backbone networks, this paper proposes a quantum switching architecture that can be applied to switch each input quantum data to its corresponding destination port correctly. The proposed quantum switching employs an efficient QMS algorithm as a subroutine, so the total execution time can be reduced in poly algorithmic time. More precisely, the quantum switching only requires n log n space consumption and can be implemented with n log n n log 2n quantum gates. Furthermore, the quantum switching achieves a better performance in the time complexity of log 3n. Based on these advantages, it can be seen that proposed quantum switching is feasible to be put into constructing high performance quantum networks. So thank you for joining my session. Hope you enjoyed it and got to know about it. So thank you and happy learning.